everyone, thanks for coming again. Today in the intro we'll be looking at kind of the basis of neural networks, like what they are and a bit about how to train them. And then also we'll do some stuff on cross-validation, which I'll explain later, obviously. So the first thing we have to know about is a perceptron. This is kind of a very simple neural network, and it's kind of what neural networks are built with. You just have like layers and multiples of these perceptrons. So let's go into what a perceptron is. At the basics, you have a bunch of inputs, then these are multiplied by a bunch of weights, and then those are put through what's called an activation function, and that gives you your output. So a very simple example, which I'll start off with, is something that looks like this. So here we have a value for x1 and x2, and then we have x0, which is 1, that's called a bias. And let's just say, for example, that here we have a weight of 0.3, a weight of 0.3, and a bias of negative 0.4. And let's suppose that x1 and x2 have to be either 1s or 0s. And I'll just put O for the output. So if x1 and x2 are both 0, what happens is we have 0 times 0.3 plus 0 times 0.3 plus 1 times negative 0.4. So what we end up here with is negative 0.4. So negative 0.4. And then what this thing here is called is the activation function. And what it does, we can choose different functions for it, but the simplest one to start off with is just the step function, which means if this number is less than 0, less than or equal to 0, then it turns it into a 0. So in this case, it will be a 0 because minus 0.4 is less than 0. If this was greater than 0, then it turns it into a 1. So it takes in inputs of 0 and 1, and it gives an output of 0 or 1. So here, that with 0, 0, the output is 0. Let's consider x1 was 1, and x2 stayed 0. We have 1 times 0.3 plus 0 times 0.3 plus 1 times negative 0.4. In other words, we get negative 0.1. And again, this is negative, so after you put it inside this step function, it outputs a 0. And hopefully you'll see that if I have 0, 0, 1, it should also output 0 because the weights are the same. Now let's have a look at what happens if both of these are 1. We have 0.3 plus 0.3 minus 0.4. And that gives us 0.2. And since this is greater than 0, after we put it through the activation function, we get a value of 1. Yep.
Can you change the weights?
Yes, you can. And that's the idea. So we want to build this perceptron to do something. And with the correct weights, it might be able to do that. So what I have here, you might not be able to see because the board's in the way, but we've created what's the OR function. So if x1 or x2, sorry, we created the AND function. So this will output a 1 only if x1 and x2 are both 1. We can do the same thing but create the OR function, which means it will output a 1 if either one of these are 1. So does someone want to suggest a bunch of weights that will get us the OR function? So we can change any one of these. And essentially, one of these just has to outweigh this one. So if I change this to say negative 0.2, then as long as at least one of these is a 1, then a 1 will be outputted here, because this 0.3 is enough to counteract this negative 0.2 to make it greater than 0. So what normally happens when we try and fit a model, and this is kind of going beyond perceptrons, but it's kind of more conceptual, is we're given a data set, and then we have to try and find the weights such that it fits our data. So before we were given the AND data set, and the weights just happen to work. But how do we find these weights? That's called Perceptron Learning, and I'll go into a bit of that later. So yeah, as I mentioned, in the very simplest case, we just have 2 inputs and 1 output. The inputs x1, x2 are either 1 or 0, and the output again is either 1 or 0. So let's talk about the geometric interpretation of our original perceptron. What we have here is this thing is just minus 0.4 plus 0.3 x1 plus 0.3 x2. And then we're seeing if this thing is greater than 0. If it's greater than 0, we classify it as a 1. If it's less than or equal to 0, we classify it as a 0. So in other words, we can plot this kind of decision boundary. Since this is very simple, it's just 2 variables, we can plot this. So this is, there's a 0.4 here. Okay, I'm just going to rewrite this into a form that might be easier. Greater than 0.4 minus 0.3 x1. And then we have x2 greater than 4 on 3 minus x1. So essentially what this perceptron is doing is checking if this inequality is true. And if we want to graph that geometrically, it look like this. So y-intercept and x-intercept both on 4 and 3, because this has a gradient of -1. And you can see if it's within this region, then it classifies it as a 1. If it's within this region, it classifies it as a 0. And if you think about the 4 possible points we have here, we have 0, 0 here, 1, 0 here, 0, 1 here, and then 1, 1 there. I might do that in a different color. So this essentially gives us a bit of insight into what a perceptron is. It's kind of like a linear classifier. And then there's also a theorem that says a perceptron can be built to perfectly classify some data if it's linearly separable. So something like this we can classify with perceptron, but something like this we wouldn't be able to, because it's not linearly separable. We can't find a bunch of weights to make this perfectly classified. Yep.
What happens if you have more than 2 inputs?
More than 2 inputs? Then it's just kind of this, but in a higher dimension. So you'll have planes.
And also, you can change the bias, or?
Yeah, you can change any of these things. Yep.
Before you change that origin color there, so it looks like that line, it will work as long as that line is separating the 3 dots on one side
Yep.
and the other one on the other side.
Yep.
How does the model decide what the slope and intercept is going to be?
Yep, that's
If
something.
given only ones and zeros going in, I mean,
Yeah.
unless
So-
you gave it some other way to measure to make it computationally faster or something. but-
Yep. So this was just kind of a toy example to show you how perceptrons work, and then now I'll get into how to actually find the weights that make it work. Yeah, actually, so I'll talk about that coming up, and then if you have any other questions, just let me know. Yeah. Talked about that. I'll get to that point. But before I do that, let's talk about this scenario where I had the orange point. So this is called the XOR case. So there's OR and an XOR, which stands for exclusive OR. And we can't use one perceptron to classify that because it's not linearly separable. But what we can do is we can add more perceptrons as well. So here we have kind of one perceptron and its output. And then we use different ways to create another perceptron. And then with these two outputs, we create another perceptron. And kind of stacking perceptrons on top of each other allow us to actually model this XOR case. And this is kind of getting into building neural networks with these simple perceptrons and adding different layers and having multiple inputs and stuff like that. But I'll get a bit more into that later. Any questions with how perceptrons work? Yep.
What's the point of using a bias unit to like change the value? Like, why can't you just have the changed value in Z1 or Z2?
Why can't you just have the changed value?
Also, like, you know how in that bias unit it says that like you minus 1.5 from Z1 and minus 1.5 from Z2.
Yep.
Why can't you just like just from the beginning do Z1 minus 1.5 and put that value in the hidden layer?
Z1 minus 1.5. Isn't that the same thing?
Yeah, I know. So what's the point of having a bias unit?
The bias essentially, so with this equation, this is the bias, right? This negative 0.4. So if we didn't have this bias, then our classifier pretty much has to go to the origin if we don't have this bias terms. And the bias just allows us to model things when it's not linearly classifiable, linear separable with a line that just goes to the origin. So say like with linear regression, you could get rid of the intercept term, but then your model's just a lot more simplified and might not be a good model. So the bias term is just allows us to draw kind of any line or any plane when you think of it in high dimensions.
So if you don't have the bias, you can't come up with a line or a plane.
Well, for example, if I have this data set, there's no way of drawing a line that goes to the origin that will separate the purple and the orange dots.
So like y equals mx plus b, right? What happens if you remove b?
It
What's
just goes
the-
to the origin.
Yeah,
Yeah.
which
So
is not what we want.
and we can't classify this example without having an intercept.
Oh, okay.
Yeah.
Alright.
Cool. Any other questions? Okay. So one last thing before I go into the learning. This activation function here is a step function because it just says 0 for less than or equal to 0 or 1 if it's greater than 0. There's different ones we can put instead of the step function. The one I'll talk about today is called the sigmoid, and it's given by this symbol, sigma, and this is the equation for it. So sigmoid of z equals 1 on 1 plus exponential to the power of minus z. So it looks kind of like an S. So at 0 it's 0.5, as it goes towards infinity it approaches 1, and as it goes towards negative infinity it approaches negative 1. Sorry, it approaches 0. And if we put a sigmoid in here, then this thing will never be 1, but it can be something like 0.9, for example. So it's something that can tell us whether it's close to 1 or close to 0. Cool. So now I'll get into how to actually find these weights. And that's called Perceptron Learning and also backpropagation when you have neural networks. But it uses a similar thing to what we did with linear regression. So with linear regression, we try to minimize the squared error. And that's what we're going to do here as well. But in linear regression, we've got an analytical solution for these set of weights globally minimize the squared error. Here, we kind of work iteratively. So if we get an error that's greater than 0, we try and think, how can we adjust the weights so that the error will go down? So again, I'm going to keep it simple, and I'm going to just assume that there's only one output in all the derivations I do, but you can easily generalize that to multiple outputs. So the one output is O, and T is the target, so what I actually want it to be. And then the error function is equal to half times O minus T squared. And for now, let's just say O and T can only be 0 or 1, but obviously that can be generalized to more things. So what we want to do is for any specific weight, so any of these weights, I want to update it to move in the negative direction of the error with respect to that weight. So this is the derivative of the error with respect to the weight. So this is the direction I need to change the weight to increase the error. But obviously I don't want to increase, I want to decrease it, which is why I subtract this derivative. This eta is called a learning rate, and that just specifies how much you want to change it each time you do. So if you change it by a lot, then you might undo some of the work that was already inbuilt into the model, which is not something you want. But if you change it by too little, then it might just take, it will be very slow, it will take a long time to actually change. And it will, actually I won't go into that. So this is the general idea. What I'm going to go into is how to actually find the derivative of the error with respect to the weight. And I think it's easiest to do that with an example. So I'm just going to look at this weight in particular, the one you multiply x2 by. So I want to find the error with respect to the weight. Now, what is the error composed of? Error is simply half O minus T squared. And then, so this is a constant, this is the only thing I can change, the output. So what's the output equal to? The output is equal to sigma, let's just call this Z, sigma Z. And what is Z equal to? Z is equal to W0 plus, so I'm going to call this W1 and W0 and W2 plus X1 W1 plus X2 W2. So we have this error which links to the output, which links to Z, which links to W2. And that's kind of the chain of how things relate to each other. So if we want to find the error, the derivative of the error with respect to this thing, we have to use chain rule. So we want to find the derivative of this first. error with respect to the output. And then I want to find the derivative of the output with respect to z. And then I want to find the derivative of z with respect to w2. So what's the EDO? And this is why I put the half here, it's because when I bring the power down, it becomes just O minus T. Now what's the O to Z? So we want to differentiate a sigmoid with respect to Z, and I'm just going to tell you that's equal to sigmoid of Z times 1 minus sigmoid of Z. But if you go back to the formula for sigmoid, and you just differentiate this with respect to Z, it's a very easy relationship that you guys can derive. So that's sigmoid 1 minus sigmoid. And then the Z, the W2, so what's that? That's X2. So whenever we misclassify something, we have this error. We want to move W2 in the negative of this direction. Going back to this formula. Yep.
Why do you only take the derivative of z with respect to W2?
Because for now, I just want to find out how I can change this weight. If I wanted to find out how to change this weight, I will take the derivative with respect to W1. If I wanted to find out how to change this weight, I'm going to take the derivative with respect to W0.
If you're doing multiple, do you do them simultaneously, or it's actually separate?
Yeah, so with each kind of iteration, so I go through this, and then I figure out how I want to change each of those weights, and I change all of them. And then I go to the next example, and then I change all of them again, and repeat this process. Any other questions? So did that answer your question somewhat, of how to actually learn these weights? Yeah. So as I mentioned, the weights are kind of what are important in perceptron and a neural network. Yep.
We see that the derivative of W0 will be 0.
Derivative with respect to W0 will be 1. Yeah, so generally we'll just go through, say, this scenario, and then update the weights. Then go to the next one and update the weights. Then the next one and update the weights. Or we can just kind of look at all of them at the same time. So go through all of these, then update the weights, and go through all of them again and update the weights. So that's how the weights are found. Yep.
So basically, you're plugging in all these inputs, finding the error, and then you're trialing it out, using trial and error. You're finding another set of weights, and the rate at which you change things is demonstrated by the learning. Yeah.
Yep. Exactly. Yeah. I wouldn't say trial and error because that kind of assumes you're just randomly guessing, but I guess like educated guesses. Yeah. That's exactly right.
Yep. Cool.
Any other questions? Cool. Does anyone want me to go through this, like why this is true, or no? Okay. Sweet. Cool. What's next? So, yeah, this is just an example of what kind of a neural network with multiple layers would look like. Today we kind of just looked at just 2 of these going to 1. That's just the classic perceptron. But say you have 3 inputs, you can make it into this big architecture like this. So this one has 2 hidden layers, an input layer and an output layer. And essentially with more hidden layers and nodes, you can just make the model more complex. And with say this architecture, if you try and do that backpropagation thing, so if you want to find out how you want to change this specific weight, you just have to apply chain rule over and over again through all these weights that this weight affects. You know what? Take this. So if you want to find out more, I highly recommend this YouTube. Well, this channel is just great in general, but this video in particular has a really good explanation of backpropagation. It goes into a bit more detail, and the example they use is a complicated neural network with many hidden layers. So if you want to learn more about that, definitely check out this video and this channel. Okay, cool. Any questions on neural networks? Yeah.
We're taking a simple example here of like one little piece, but then obviously you're saying you can build very complex things by using a lot of them.
Yep.
How do they kind of predict the behavior of a lot of it going on? Is it sort of like an induction type argument?
What do you mean predict the behavior?
Well, like we can model clearly here how one of them works.
Yep.
But then the way they interact, if you put a bunch of different hidden layers or different nodes at each layer.
So like
How
what
do
does
they
each
do-
node contribute to the model and how they
Yeah.
work together too?
Because clearly it's, you know, I guess, yeah, I'm just wondering how you model the interaction of all of these things.
Yeah.
It's probably not too complicated, because.
Yeah. So short answer is you don't. So neural networks is one of those things that work just because they work.
Yeah,
Like,
yeah.
from my understanding, no one's really been able to. There's some kind of intuitive explanations. Actually, I mentioned how you can think of just one of those things as a linear classifier. So that's only useful for like classifying linear things. So if you kind of combine two of them to another one, you can kind of think of that as trying to like classify using a curve or a corner. And so yeah, like I don't think there's any set really rigorous way of thinking about how they interact with each other, but there are these kind of intuitions.
I mean, yeah, I mean, there must be some, because, what's your name again?
Daniel.
Daniel. Yeah, he was alluding to, you know, there's certain proof about that, you know, any sort of function can be modeled by this type of thing, as long as you have enough layers and nodes.
So wait, what was your question is
Well,
how?
for example, last time you said,
Yeah.
if you didn't have the activation function, then all of this would just collapse into
Into a
one
linear
linear
regression.
transformation.
Which is yeah,
So,
correct.
but by adding these other non-linear little,
Things that
which
it,
kind of compress the data or twist it in weird ways, so it's kind of like you're getting a linear function with an output that looks like it's not, because
Yeah.
it is not, but,
yeah, because of the activation function.
yeah.
Because we said like how what a neural network is essentially doing is just a rotation, stretching and rotation, right?
Yeah.
And then that's the problem. If you just keep using linear, then it's just a combination of rotation, stretching, rotation, rotation, stretching, rotation. But if you do two rotations, isn't that the same as doing one big rotation? So that's why it's a linear regression. But yeah, so the activation function actually changes the process. It does a rotation, stretching, rotation, and then it truncates the function, and then it does a rotation, stretching, rotation. But that means it's different from the original one. So your question was like, how does it model the interactions? So because they do, so you know these are just matrix multiplications. So it's essentially doing, remember last time we used we showed the TensorFlow playground thing. Also the first lecture, we showed you like how you can classify boundaries and stuff. It was on the TensorFlow thing. And also what you can do is, you know the input, the theory of neural networks says that if you can model any single function without actually changing the input, so you only need to have two columns. You don't need to do the column squared, or you don't need to do the sign of the column. But if you do want to do the sign of the column, it's the same as doing neural networks. So it's essentially modeling the sign inside the neural network.
Sure.
Yeah, I don't know if that
Yeah, I need to formulate my questions better, so you can go on.
Yeah. Well, I'll just kind of talk a bit about it. Yeah. Generally, one of the things that I said about neural networks is that they're a bit of a black box. You kind of just feed it data, and then it just gives you something that's pretty good. Like you look at some of the things that neural networks can do, like image classification, all that kind of thing. It's quite amazing that, you know, just a bunch of nodes that's just a linear combination and an activation function. Like a whole bunch of that can give you an output that works. It's pretty amazing, but yeah, it's been criticized because it's just kind of a black box. It works because it does work. And yeah, so it's a bit of an unsatisfying answer.
I'll probably discuss about it later. Yeah, later if it depends. Anyways, yeah, keep going.
Okay, cool. Any other questions? Okay, sweet. So the next thing I'll talk about is, say we have this architecture, so have two hidden layers, which each of them having 4 nodes. How do we know, why do we choose this architecture compared to another one? Why not have just one hidden layer with 8 nodes, or 3 hidden layers with 2 nodes, that kind of thing? And yeah, as I mentioned, neural networks, they kind of work because they work, so we just have to see which one works the best. But how do we do that? Well, this is coming back to, what is a good model? How good is a model? So here I just have a dummy bunch of data points with a linear regression to it. And I'm telling you that this, I'm calling model 1, this linear regression, has a mean squared error of 7.35. Now, I'm going to introduce a new model, model 2, that has a mean squared error of 3.2. So the question is, which model is better? So
Is this mean squared error is on training data only?
we just have this data. Yeah. So which one is better? Would you reckon?
Can't say.
Can't say, why not?
Because we don't know how to perform on new data.
Yeah, exactly, that's exactly right.
If it's modeling based data, it's like of no use if we can't model that new data.
Yeah, great. So model 2, I have this kind of 5-degree polynomial, and it has a smaller mean squared error. But yeah, it comes back to overfitting, and I'll explain about that next. Basically, just intuitively, when you look at data like this, you probably think, okay, it's a linear trend. And what I want to say is, with a more complex model, we can always make it look more like the data. So here I just have 2 parameters, the intercept and slope. So it's a model that's fairly simple. Here I have 6 parameters. And because I can tweak and adjust those 6 parameters, I can make it a lot more complicated and can fit the data a lot better. But then we get into the problem of overfitting. So this is an example of overfitting. Here the mean squared error is 0 because our model goes through all of our data points. But what's bad about this model, as you mentioned, is that it probably doesn't do well on unseen data.
High
So
variance.
exactly, like if we're given the exact same data, then yeah, it'd probably be a better model. But we normally want to use our existing data to try and model unseen data. So how do we actually determine which of these models are better? We just have to test it on unseen data. So how do you test on unseen data? Essentially, you just have to split the data into a training and a test set. So for example, here we have 2 models, the green model and the orange model. And we have 2 data sets, the training data and then the test data. So the training data is what we build our model with. And you can see, obviously, the green model is a lot simpler than the orange one. It's more smooth. Whereas the orange model is a lot more complicated and tries to fit to the training set too much. So what we do is then we test it on our test data. And we use our green model to try and predict on the test data, and our orange model to try and predict on the test data as well. So you can see here, the green model generally seems to be in the right vicinity of our unseen data, the test data, whereas our orange model kind of jumps a bit all over the place. So for example, this data point here, it predicted, thanks Daniel, it predicted up there. This data point, it predicted down there and stuff. So if we look at the mean squared error of the test set, we'd probably find that the green model is better than the orange model. So how can we split things up into training and test set? Cross-validation is a very common method. So basically, this is called a 5-fold cross-validation because you're splitting the data into just 5 random chunks. And then for one experiment, you train on the white data, the training data, and then you test on the orange one. And you obtain some kind of cost function, so most likely mean squared error.
Can we randomly choose 20% from the original data as data?
Yeah, no, that's essentially what we're doing.
But this one is taking the first 20% and the second 20% and so.
Okay, yeah, no, that's a good point. So ideally, we'd want the data to be as random as possible. So, like good practice probably is just randomize your data and then take like the first 20, because then it's the first 20 of a randomized data. So it's essentially random data. And then you just repeat this, but use a different fifth for the test set and different 80% for the training set, just so you kind of get like more situations of test and training set. Because if you just do one of these, then maybe just by chance, the random bit you chose, there was some heavy bias towards it and it doesn't give you a good result. So this just kind of allows you to do the same experiment over and over again for reliability. So how do we avoid overfitting? Well, let's go through what we know already. Complex models will fit the training data better because there's more parameters you can tweak. Good models perform well on unseen data, and unseen data is the test set. So essentially, you want the model that does the best on the test set. Now what this graph is showing is on the x-axis we have increasing model complexity, and on the y-axis we have prediction error. Now let's look at the blue line first. So as we increase the complexity of the model, the prediction error for our training data goes down, because that alludes to our first point. Complex models can fit training data better. So this will pretty much always be decreasing. But this is the test data. You can see as we increase the model complexity, the model can do a lot more things. So say a straight line compared to a linear regression. A linear regression can model a linear relationship between two variables. Then if you go to a parabolic model, it can model any parabolic relationship. And with the cubic, you can just change it more and more. So if your data actually requires a parabolic model or a cubic model, then it'd be better than, say, linear regression. So increased model complexity is good up to a certain stage. And you can see here, as model complexity increases, prediction error improves. But it gets to a point here where as you increase the model complexity, the test data prediction error goes up. And that is basically the point where you realize that your model is overfitting. It's doing well on the training data because it's just looking at those training points. But when you use it on unseen data, you get a situation like this, where it models the training data really well, but it wouldn't do well against the test data. So how do you decide which kind of architecture to use? You'd essentially kind of build one architecture and then test it on the test set using cross-validation or whatever. Build another one and then test it again, and this is a bit of a manual process. But yeah, you just see which one has a nice test error. And with some models, like for example, random forest or GBMs, which I don't expect you guys to know because we haven't covered that, you can actually kind of improve the model bit by bit. So you can actually get the program to automatically increase the model complexity without you having to fiddle around with the architecture or whatnot, and run all these tests and get a graph that looks kind of like this. And some packages where can allow you to kind of tell it to pick this bottom point where it has the best test data just before it starts overfitting. So that's the idea behind cross-validation overfitting. Does anyone have any questions about that? Cool. Okay. So that's it for the intro. We'll have a bit of a break, and then Daniel will talk about his advanced stuff.
Yeah, so there will be full programming in the advanced ones.